Hi, this is the second episode concerning this radar seeker 9E420. This radar seeker was used in different missiles. In the first episode, we have seen this board on the screen. Today we are going to see another board, which is this one on the screen. We can see here the complete seeker. We can see this board we will analyze today. There is another identical board here for the second motor. The board of the previous video is on the back of that seeker. We cannot see. Oh, this is the board. I have removed the shield here. Inside there are two transistors here. There are several op-amps. Here we have a quad analog switch, and this is a quad NAND gate. We have here two power resistors, 0.1 ohm. This board is cut here, but I think it's repairable. This board comes from the seeker we have seen on the picture at the beginning of the video. So there are two identical boards on the seeker, one for each motor. I did the complete reverse engineering of that board. There are two different circuits. The first circuit is the amplifier we can see on the screen. The input is here. The input is an AC voltage, and the signal is fed to this voltage follower made with the Q11 here. The output is fed to this transistor Q10. You can think that it is a voltage follower, but it is not the case. You can see that there is no bias on the emitter. Actually, this transistor is used as a chopper. If you follow my videos, you know that a chopper uses a transistor which works in reverse mode. This transistor is used actually as a synchronous detector. The AC voltage which is present on that line is converted into a DC voltage on that line here. The DC voltage is fed to this low-pass filter. This filter is a second-order low-pass filter with a cutoff frequency of 10 kHz approximately. We can see the response curve here. The DC voltage is fed to this circuit, which permits probably to have a phase correction. And this voltage here is fed to this amplifier. The gain of the power stage here is defined by these two resistors. Okay, so therefore here we have a gain of approximately 7, and the output is a DC voltage here. So what can be the purpose of this amplifier? We can see on the antenna mechanism, which is here on that picture, we have two rate gyros here. This one and this one. We have also two accelerometers. Okay, and there is of course one motor for each axis. It seems clear that this amplifier is used for the rate gyro. So here there is an image of a classic rate gyro. So we can see here the speed axis of the gyro. Okay, on the wheel here. When there is a variation of the angle along this axis, there is actually a torque provided by the gyro along this axis. So the goal of that system is to compensate this torque using a torque motor, which is here. Okay, so there is an assembly of coils and some magnets also. So the goal is to keep the same position of the gimbal here. This is done using a peak-off here. This is a zero detector, a kind of differential transformer. When the gimbal is centered, there is a null voltage at the output of the peak-off sensor. When there is a change of the angle velocity, there will be an error voltage. This error voltage is amplified, converted into a DC current, and this DC current is fed to the torquer coils, which permits to provide a torque in order to retrieve the null position here. So this is the goal of this amplifier. The peak-off error signal is fed to the input of this amplifier, and the output DC voltage here is fed to the torquer coils. Okay, we can see an image here of this rate gyro. The reference of the gyro is DUSV4230A. 30 means that the maximum range is 30 degrees per second. This is the second part of the schematic. This is a servo amplifier for one DC motor. The motor is here on the right. These two power Darlingtons are external. We can see these two transistors here. The servo motor is here. This is a classic amplifier. There is a current limitation here using these resistors. This one And this one here, the current limit is approximately 8 amps. It corresponds actually to the starting current of the motor according to the datasheet, 8 amps. Now, there are several inputs. One interesting input is this one here. You can see that this input can be disabled using this analog switch here. We can see that we have an integrator, okay, the feedback capacitor here. And this capacitor can be discharged using this digital input. The zero of the integrator can be adjusted using this trimmer. The integrator has three inputs, two inputs here using these two resistors, and there is another input using these two resistors. There is also a damping circuit using these capacitors and this resistor, and there is a gain adjustment. I think that this input is the return current of the torque motor of the red gyro. The current is translated into a voltage, and this voltage is translated into a current which is fed to the integrator here. Therefore, at the output here, there is an image of the angle. The signal is fed to the servo amplifier, so this permits to compensate the rotation of the missile itself. This input is probably connected to the feedback potentiometer using a voltage follower, which is on the other board. I think that this signal is the input signal which permits to set the angle of the antenna in one axis. This signal permits to set the angle to 0. This is a kind of home position. At least it is what I think. And this one has seen better days, but I think it is in working condition. You can hear the displacement of the gimbal. The range is limited, of course. On the rear, there are several terminals. You can see that some pins are connected together and connected here, which is obviously the ground. I have measured the resistances. You can see it is very easy to find the gyro rotor here. There are three resistances of 42 ohms. Probably the voltage is 36 volts, 400 hertz between each phase here. So you can see that there are 4 coils. The 3 coils has a common ground here. Okay, and one is totally isolated. This one should be the torquer, because normally we should have a current shunt between one point and the ground. Okay, but we can test by applying a DC current between these two terminals and see if we can hear the gimbal moving. Okay, so I have connected these two wires to a current source of 50 milliamps. This should be a safe value. Okay, I did something wrong. This coil is not here, but here. Okay, so you can hear. Okay, so this is the torquer. Okay, so we should have the zero detector, the peak off. Okay, so it can be any of these coils here. So I will apply an AC voltage between these two terminals. Okay, so I have found the peak off. One winding is this one, second one this one. So I have applied here an AC voltage, 400 Hz, 2 or 3 volts RMS or something like that. And I have connected to this winding the oscilloscope, which is synchronized to the function generator in order to be able to see the phase. Okay, so you can see that we have a phase reversal. Of course, it is difficult to have zero because this thing is unstable. Maximum amplitude is 400 millivolts peak to peak for an excitation voltage of 8 volts peak to peak. The remaining winding is this one here, okay, which seems totally isolated from the other windings. So I don't know exactly what is the purpose of this one. It is maybe for self-test to provide the torque in order to test that device without moving the gyro. Okay, so effectively this coil permits to generate a torque. Okay, so you can hear.
Okay, so the torquer is here because it should be isolated, and this is actually the test winding. Okay, so this permits to generate torque. Okay, so now we have everything.